Hello students, welcome to another session of online class. Today we are going to discuss a very important topic in the second module, that is called the central limit theorem and law of large numbers. So our today's objective is to revise what we have studied in the last class and see what is the law of large number and what you mean by central limit theorem, and we will discuss some problems regarding to central limit theorem. So going to the revision, in the last class we have studied two topics. One is the sum of two independent random variables. If two random variables are independent, for example x and y, then their sum is represented as w, which is x plus y. Then its probability distribution is the convolution of first one and the second one, and its distribution function, cumulative distribution function, is given by minus infinity to infinity, and for y the limit is minus infinity to w minus x fxy of xy dy dx. So minus infinity to infinity is the limit for x, and the mean of w will be mean of x plus mean of y, and variance of w will be variance of x plus variance of y, and the characteristic function of w will be the product of characteristic functions of x and characteristic functions of y. Now this is used in our electronics mainly when we deal with the voltage which consists of actual voltage along with the noise. Here v of t can be treated as x and n of t can be treated as y. Then they are added, then their property can be studied using these equations. Similarly, we have IID process, identical independent distributions, where xi is different same distribution, identical distributions, but they are independent. Then if they are added up together, we have w is equal to summation I equal to 1 to n xi. Then since they are identical, the mean of each one will be corresponds to general mu x, and variance of each one will be sigma x square. Then the mean of this sum will be mu w will be n times mu x, and variance will be n times sigma x square, and the characteristic function will be nth power of x, characteristic function of x. So these are the things we have studied in the last class. Now moving to our today's topic, the first one is law of large numbers. So we will consider an experiment. Toss a coin 10 times and observe the number of heads. Repeat this experiment n times. So what we are doing is, the first time we are tossing the coins for 10 times. So that experiment is represented as x1, random variable x1, where x1 is the number of heads in the first experiment. Now this first experiment means here we are tossing the coin for 10 times. Second experiment, repeat this one again 10 times I am doing. That time how many heads I got, that will be represented as x2. So ith experiment xi and nth experiment xn. Now there is a question, what is the distribution of x, and whether xi is IID process or IID random variable. So what is the distribution of x? We know that this is binomial distribution, so there is a mistake here. This will be binomial distribution binomial with the n equal to 10, number of observations are given. So tossing the coin means there is a success or failure, so p is equal to 0.5. so this is repeated n times, so that will be n is equal to 10. So the mean will be n times p, that will be 5. We know that for the binomial distribution the mean is given by np, so that will be 5. So what does this mean? When you toss coin 10 times, we expect that 5 heads will be there, because 50% is the probability, right? 10, the 50% of 10 will be 5. So it may not be 5 when we do the experiment actually, because if you toss coin for 10 times it may not be 5, but we expect that 50% of them will be 5. That is why expectation means. Now, does this experiment is IID, independent and identically distributed? Yes. Why? Because for the first 10 coin toss does not depend on the next 10 coin tosses and like that. But each 10 sets of tossing of coins are identical, because in the first time which coin is used, the same coin is used the second time also. So this is what we do. So this is an IID process, and this is a binomial process. So all the 10 experiments what we are doing are binomial experiments. So we will see a simulation regarding the same experiment, because we cannot toss the coin here. So we know that probability of heads is 0.5 and I am tossing the coin for 10 times. So I have true probability is given in this green line. You can see here, that is 0.5, that is proportion of heads. So 10 into 0.5 means 5 will be the mean, expected mean, actual mean. Now I am tossing the coin for 10 times. See here, in the first toss for the 10 times I got 8 heads and 2 tails. It is a random process, so I cannot tell how much I will get. Now I am tossing this one again. Now total number of observations become 20. If you see, out of 20, again doing that experiment, the total number of heads become 13. Now if I repeat this process for many times, I am repeating this process for many times, so you can observe here, initially number of heads was higher and it decreased and decreased, and I am moving or increasing the value. So this is 70 experiments. If I do this one for like this one for 1000 or 100 or 1000 experiments, what I can expect is that this blue line of graph will converge to this green line, means it will come very closer to this green line. See here, you can observe this one. Now the value almost, the expected value is 0.5. It reached 0.54, 0.55, increases, decreases. But as you do this experiment for very large number of times, what you can see is it will become exactly half here. So that is what we modify as law of large numbers. So from this experiment what we understood that is as the number n increases, the average of the experiment tends to the actual average of the population. So we will discuss in as a theorem this one. So consider a random variable x1, x2, xn. The sample mean is denoted by x bar is equal to x1 plus x2 plus etc. xn divided by n. I can write this one as summation xi up to n, right? So 1 by n is taken outside, then 1 by n is given inside, so that it becomes xi by n. So summation xi by n, x bar is equal to summation xi by n. So this is x bar actually, x bar equal to summation x by n. Now assume that this is some new letter, for example y. Now what is expectation of x bar? That will be mean of x bar, right? So in the last class we have seen that it will be n times the mean of y. So if this is y, then n times mean of x by xi by n. So this is a linear, expectation operator is a linear operator, so I can take 1 by n outside, so that will be 1 by n expectation of x, that will be mu x by n. So n cancels, so what you are getting is mu x. So similarly variance of x bar is also n times variance of xi by n. Now variance of xi by n, x by n is same, but variance is not a linear operator. So what happens is there will be sigma x square by n square will be there. So this n cancels with the n square and you will get sigma x square by n. So this is very important. Expectation of x bar will be mu x and variance of x bar will be sigma x square by n. Now based on this, the theorem or the statement is the law of large number says that if x1, x2, x3, xn be IID random variable with a finite expected value of e of xi is equal to mu, then for any epsilon greater than 0, any epsilon means epsilon can take any value, then the probability of x bar is minus mu x greater than or equal to epsilon is equal to 0. This as n tends to infinity, this happens as n tends to infinity. If you see the simulation graph also, you can observe that initially the average was not nearer to 0.5, but as you move on increasing the number of experiments, x bar was very closer to mu x. So x bar minus mu x becoming more than 0 is almost 0 as n tends to infinity, or otherwise we can say that as n tends to infinity, the sample mean means x bar, we are doing the experiment and take the samples, right, is always tending to the actual mean of the probability distribution. So mu x is the distribution mean, x bar is the mean we do by doing the experiment. So if we assume the proof for this statement is simple, so there is something called Chebyshev's inequality, so which says that probability of something greater than or epsilon is always lesser than or equal to variance by that particular term. Here it is epsilon, so that will be epsilon square. Now from this one we have variance of x bar is sigma x square by n, so substituting that one here, it will be variance of x bar will be variance of x by n by into epsilon square. Now as n tends to infinity, this term will become divided by infinity, and so this becomes 0. So that is what the proof for this one. So proof is simple. So this is law of large numbers. So law of large number, as a summary we can say that as the n tends to infinity, the sample mean or the mean which we get by doing the experiment tends to the actual mean of the distribution what we consider. So simply, if tossing the coin, we expect that 5 should be the number of heads if we toss the coin, but actually we will not get. But if we do the experiment repeatedly many times, the average will be 5 only. So that is about law of large numbers. Now the next topic is central limit theorem. So to understand central limit theorem, we will do another simulation. We will go for another simulation. So I will give the link for each simulation websites which is there. So in this one, so I am considering a parent population, means which I am considering as some experiment which has 32 outcomes and their probability are randomly given here. So I can design something. So here if you see that 0 is less occurring and this value is most occurring and this value is less and somewhere it is not at all occurring. So this distribution, can you tell me which distribution is this one? Is it a normal or a Poisson or something like that? It doesn't resemble any graphs which we studied, right? So this is not a distribution. I am calling this as a custom distribution. So I am designing my own distribution like this one. So this is a custom distribution. So in this distribution, if you can see, this is marked here. The mean is blue color and the median is pink color. We observe only mean here. So now this is the entire population, means 0 to 32 outputs are there. From this one I am taking some 5 samples, okay, 5 samples, and in another experiment I am doing 2 experiments at the same time. In another one I am taking 10 samples. So if you can see here, from the most probable regions samples are taken. 5 samples are taken. So the mean will be 5, and sorry, here I have to take the mean also. So animated, first 5 samples are taken, mean comes here. For the 10, the mean comes here. So what is this one? The mean is here, but if I take the sample, the mean comes here and here. So this is one experiment. Now I am taking 5 times, this is repeatedly. So you can see here the sample means are distributed like this one. So first, second, third, 5 times I have done. So this one, total repetition 1 I earlier did, and totally 6 repetitions are done. Now again 5 I am doing. So can you see this one, this blue colored one, that is the mean. Actually it was 16.86 here, this is 15.58, here it is 16.15, and one more 5. See, the mean is shifting towards the 16.86. Now I am doing a large number of times this experiment, for example 10,000 times. Can you see the mean is shifted to 16.90, here it is 16.93. Again I am very large number, and you can observe the mean is here, which mean comes in a same line. So, but one more thing what we have to observe is here that the distribution which we taken earlier is unknown distribution. We don't know what type of distribution, but the mean of that one comes to a particular shape. Do you know what is this? What this shape is called, or what this distribution? This kind of distribution is called a Gaussian distribution or normal distribution. So what we observed is unknown distributions. Sample mean means we are taking some sample set, some elements only from that one, and doing the calculating the mean and checking what distribution does that mean has. And if you observe that one, the mean is always distributed as a normal or Gaussian distribution. So that is what central limit theorem states. So if x1, x2, xn in IID processes with the E of xi as mu and variance is sigma square, then we can define a random variable z, which is x bar minus mu divided by sigma by root n, which is nothing but x1 plus x2 etc. xn minus n mu by root n sigma, converges in distribution to the standard normal random variable as n goes to infinity. As we seen in the simulation, here also this is the statement, this x bar minus mu by root n sigma, or sigma n by root 10, sigma by root 10, always converges to a standard Gaussian distribution. So what is standard Gaussian distribution? Is nothing but with the mean 0 and variance sigma. So otherwise we can say that limit n tends to infinity, probability of this one lesser than or equal to z is phi of z. This we know for normal distribution, this is phi of z is the expression which we call is the standard normal cumulative distribution function. So this is very important. So using this theorem we have to solve different problems. So how to solve that one is given here. So for example, what we have to do is identify which is the x, and from that you can write y is the sum of that x variables, then expectation of y will be n times mu x because IID process, and variance is n times sigma x square, then standard deviation is root n sigma x, because square root of this one will be root n sigma x. Now central limit theorem says that you can shift the y by mu y and divide by sigma y, that is n mu x by root n sigma x, then this will be approximated to normal distribution. Then probability of y1 less than y2 can be shifted like y minus mu y or it will be phi of y2 minus mu y by sigma y and phi of y1 minus mu y by sigma y. So our steps we will understand while doing a problem properly. So one of the example, see here, a bank teller serves customers standing in the queue one by one. Suppose that the service time xi for a customer I has mean e of xi is equal to 2 and variance of xi equal to 1. We assume that the service times for different bank customers are different. Let y be the total time of the bank teller spends serving 50 customers. Find the probability that total time a bank teller has to spend in is between 90 to 110 minutes. So we will analyze the question. A bank teller serves the customer standing in the queue one by one. So those who are, many customers are in the queue and their service time is a random time. We don't know how much time it takes to serve a customer. So each customer, the mean average time required is 2 minutes. So can I write e of xi or mu x is equal to 2, and variance of x is 1, that is also given. So what we have to do is, the different customers, the time required are independent and each customers are identical because they follow the same queue. So identical and independent, so that will be an IID process, and we have to find the total time. So we have to add all the times of individual customers waiting time. Total time means, right? So y is equal to x1 plus x2 plus x3 plus. So this is nothing but sum of IIDs. Now what we have to do? We have to find the probability that total time a bank teller has to spend is between 90 to 110 minutes. So you have to serve 50 customers. So we have n is equal to 50, and what we have to find is probability of 90 to 110. Why? Total time means adding the time of each customer. So how to do that? So these are the given values. Then as we discussed here in the steps, what we have discussed in the steps, first we have to find mu y and sigma y, right? So mu y and sigma y can be calculated as mu y is equal to n times mu x, because sum of IID process means n times the mean. So 50 into 2, that will be 100, and sigma y is root n sigma x, so that will be root 50 into 1, that will be root 50. Now we are modifying our variable y to z as y minus mu y by sigma y. This we know in normal distribution we can approximate to, as n increases we can approximate to normal distribution, right? So I am approximating y to a normal distribution. So y minus mu y by sigma y, so that will give this will be the variable z. Now y1 was 90, so 90 will become z1 with the value 90 minus mu y is 100 divided by sigma y is root 50, that will be minus root 2, and z2 is, second part should be converted to shifted by mu by 100 and divided by, scaled by root 50, that will be 110 minus 100 by root 50 will be root 2. So instead of finding probability of 90 less than y less than 110, it is converted to standard distribution of standard normal distribution of finding probability of minus root 2 less than z less than root 2. So probability of minus root 2 less than z less than root 2 is nothing but upper minus lower. So phi of root 2 minus phi of minus root 2. So phi of root 2 minus, whenever you have phi of minus z, you have to take 1 minus phi of z. So that is why 1 minus phi of root 2. So that will be 2 into phi of root 2 minus 1. So as we discussed in the previous normal distribution video, you can refer that video once again. To find the phi of 1.414, you have to check the table and subtract 1 from that one, you will get to the value 0.8427. So this is how we find the value of the total time a bank teller has to spend between 90 to 110 minutes. Now we will discuss another type of problem, because this is very important. Central limit theorem is very important as we go for this one. Consider a communication system. Each data packet consists of 1000 bits. Due to the noise, each bit may be received in error with the probability of 0.1. It is assumed bit errors occurs independently. Find the probability that there are more than 120 errors in a certain data packet. So we analyze the question. Given 1000 bits are transmitted and each bit sending is independent, means the first bit is sent, the second bit does not depend on the previous bit, so they are independent. So each bit to sending each bit is either will be success or failure. So what kind of distribution is that one? Only one bit is sent at a time, right? So there is no n is equal to 1, but the probability of success and failure is given, that is 0.1 or the success is 0.9. So this distribution is a Bernoulli distribution with the value p is equal to 0.1. But such experiments are 1000 bits are transmitted, so n will be 1000. So we have to find the total error, right? So to finding the total error means you have to add all the cases. So x1 plus x2 plus x3 plus xn. Why we are adding? Because it is identical and independent. So this will be summation of IID process. And what we have to find the probability that there are more than 120 errors. So probability of y greater than 120. So since this is a Bernoulli distribution, the mean of the Bernoulli distribution, so we have to go back for our distributions. Just check your notes. You can see that for Bernoulli distribution, mean is p, that will be 0.1, and variance will be this should be sigma x square, will be p into 1 minus p, that will be 0.1 into 1 minus 0.1, 0.09, and its root value will be 0.3. Now, as we said, the first step is to find mu x and sigma x. Sometimes it will be given in the problem. Here it is not given. So we have to identify which distribution is this one. From the distributions expression, you have to calculate mu x and sigma x. Once it is done, we go for finding mu y and sigma y. Y is actually added values of all x's, so that will be n times mu x and root n times sigma x. So n times mu x means 1000 into 0.1 will be 100, and this will be root 1000 into 0.3, that will be 90, root 90. Now we assume that according to the central limit theorem, according to CLT, central limit theorem, we can modify this into a normal distribution with z is equal to y minus mu y by sigma y. So when z transforms by shifting by mu y and scaling by sigma y, even the 120 also transforms to 120 minus mu y is 100 divided by root 90, that will be 20 by root 90. So once it is done, we calculate probability of y greater than 120, that will be probability of z greater than 20 by root 90. So that will be greater than means we have to find probability of z less than 20 by root 90. So probability of z less than root phi of 20 by root 90. So 1 minus phi of 2.11, if you check the table, it will be 0.0175. So this is how we solve the problem. So we discussed two types of problem. One case where the probability mean is directly given. In another case, distribution is given and you have to find the mean. So this is how the central limit theorem. This is all about the central limit theorem. Thank you.